Alright, so in this video we will review centripetal acceleration and force and go over exactly what we will need to know for our test. If we look at the image to the right, we can see an object moving in a circular path. Now, if we label this figure as, let's say, 1, 2, 3, and 4, we could represent 1, 2, 3, and 4 as instantaneous snapshots of the object. So what can we see about each of the positions? Well, at position number 1, we can see that we have a velocity vector moving towards the right. So the object is moving towards the right and wants to continue moving towards the right, but can't. And why is that? Well, because there's an acceleration that's pointing downward. Let's move on to position number 2. At position number 2, the velocity vector, or the object, wants to move downward, but can't. Why can't he move downward? Well, there's the same acceleration pointing to the left. Let's look at position number 3. We have a velocity vector moving to the left, so the object is want to continue on that trajectory, but can't, because there's an acceleration vector pointing, again, up. And finally, at position number 4, we see the object with a velocity vector upward, but does not move upward. Why? Because there's an acceleration moving to the right. Upon further analysis, we can see that the accelerations aren't moving down, left, up, and right, but instead are moving towards the center of our circle. So what does that do? Well, that does a lot to our object. It keeps our object in that circular motion. It doesn't allow for the object to continue on the trajectory where the velocity vector wants to go. In each of the positions, we can see the velocity is trying to move in a different direction, but can't because there's an acceleration also working on the object that's pointing towards the center. Now we know from Newton's second law of motion that an object which experiences an acceleration must also be experiencing a net force. And in this case, we call this force centripetal force. The centripetal force is equal, so we'll go force centripetal is equal to the mass times the acceleration centripetal. So what do we know about the centripetal acceleration? Well, we know the centripetal acceleration, the AC, is equal to the velocity squared over r. So if we put that information into our F equals ma, or the force centripetal equals the mass times acceleration centripetal, we get that the force centripetal is equal to the mass times velocity squared over r. So what exactly is that force centripetal? Well, that force is what keeps the object moving in that circular motion. Well, for our Regents class purposes, we need to understand what the equation is really showing us, or really telling us. Well, if we write that equation bigger, let's take that equation, let's really write it big so we could analyze it. If we have the force centripetal equal to the mass times the velocity squared over the r, what happens when we, let's say, double the r? Well, what exactly is the r? Well, the r is the radius. So going back to our picture, we can see that the r is labeled right here. I'll just box it so you can see. There is our r, and that's the radius of our circle. So what happens when we double the r? Well, if we look at the equation, we can see whatever we do to the right-hand side, we must do to the left-hand side. So what exactly do we do to the right-hand side? Well, we added a 1/2. As much as we doubled the r, we also added 1/2, or multiplied the right-hand side of the equation by 1/2. So since we multiplied the right-hand side of the equation by 1/2, what must we do to keep this equation the same? Well, we must add a 1/2 to the left side of the equation to keep it equal. So what do we see? We see that the force centripetal is inversely proportional to the radius. Now put in parentheses r. Okay, that's the first thing we need to know. All right. What else do we need to know? Well, let's rewrite the formula. And let's put force centripetal equal to the mass times velocity squared over r. What happens when we, let's say, double the velocity? So if we make the velocity, we double that, we put a 2 there. What happens to the force? Well, let's think about this. When we double the velocity, this equation could be written, or has to be written, like this. Double the velocity squared. Now, can we write this equation differently? Yes, we could write it equals m times 2 squared times v squared over r. I'll just put that there so you know exactly what's going on. Now, those two equations are equal. So what do we do? Well, we have an extra 4 on the right-hand side of our equation, right here, from that 2. So if I was to just erase that really quick so you could see, we added that 2. 2 times 2 is 4. So in order to keep this equal, we must add a 4 on the left-hand side of our equation. So what does that do? Well, we doubled the velocity, but we quadrupled the force. So the force is directly proportional. So force centripetal is directly proportional to velocity. Now we must realize, even though they're directly proportional, doubling the velocity does not double the force. It quadruples the force. So we have to remember that we must remember what we change the velocity squared by we must do to the force. Okay? So let's try some examples. I'll write the equation up here again. So force centripetal equals the mass times velocity squared over r. Okay, so if we half, let's say we half the r, what happens to the force centripetal? Well, since we half the r, it's inversely proportional. So we must double the force. What happens if we, let's say, quadruple the radius? What happens to the force centripetal? Well, we quadruple the radius. It's inversely proportional. So we quartered the force. All right. How about if we, let's say, quartered the radius? What happens to the force centripetal? We quartered the radius, so we have to quadruple the force to keep them consistent or equal. Okay? Knowing this, we could pretty much answer any word problem that the Regents gives us. All right, let's try for velocity. What happens now velocity-wise? All right, so if we double the velocity, what happens to the force? We did that on the last page. Remember, the force changes by the square of the velocity, so we quadruple the force. What happens when we half the velocity? Directly proportional. However, it's to the square of the velocity, so we square 1/2, and what do we get? We get that the force centripetal has to be quartered. Okay, what happens when we quadruple? We quadruple the velocity. What happens to the force centripetal? Well, we quadruple the velocity. So, we must multiply the force centripetal by 16, because 4 squared is 4 times 4, which is 16. And finally, what happens if we quarter the velocity? Directly proportional. The force centripetal must be multiplied by 1/16. Alright, so let's look at a question. An 800 Newton running back turns a corner in a circular path of radius 2 meters at a velocity of 8 meters per second. Find the running back's mass, centripetal acceleration, and centripetal force. Alright, so the first thing we want to find is the running back's mass. Well, how do we find that? Well, it says an 800 Newton running back. So we'll underline that. If we have an 800 Newton running back, what is that in kilograms? What's his mass? Well, we know that force equals ma. And since 800 newtons is our force, so we have 800 newtons equals m. What's our acceleration? Well, the acceleration due to gravity is, we could substitute 9.8 meters per second squared. If we divide by 9.8, and we divide by 9.8, we get that the mass must equal 81.5 kilograms. Alright, so now that we know his mass, we knew his weight, but now we know his mass. Now we must find the centripetal acceleration. So in centripetal acceleration, as we've learned, is AC equals v squared over r. So what's the information that we need to know? Well, we know that the radius is 2, and we know that his velocity is 8 meters per second. We can underline that in the problem. So we know that the radius is 2 meters, and his velocity is 8 meters per second. Again, we can see that we can solve for centripetal acceleration because the running back turned a corner in a circular path. When you see circular path, I'll underline that in green. When you see circular path, you know that we are talking about some type of either acceleration, centripetal acceleration, or centripetal force. So we have the centripetal acceleration equation. We could put 8 meters per second in for v. That needs to be squared, and our r is 2 meters. When we work this problem out, we can see that 64 meters per second is over 2 meters. So our centripetal acceleration must be 32 meters per second squared. Make sure that 2 is good there. And I could box in this answer. And I'll also box in the answer of the running back's mass. Now to find the centripetal force, we know the equation F sub c, centripetal force, equals the mass times the acceleration centripetal. When we substitute the information, we get Fc equals the mass, which we found to be 81.5 kilograms, and the centripetal acceleration, which we found to be 32 meters per second squared. When we multiply them together, we get that the centripetal force equals 2,608 newtons. I will box that. So that's how you find the mass of the running back, the centripetal acceleration, and the centripetal force for this problem.